Okay, good morning. My name is David. I work with Todd Coleman in the Brain-Computer Interface Lab here in the Beckman Institute on brain-computer interfaces. And although I'm in the electrical engineering department, and this is, I think, a signal processing session, most of my research in electrical engineering actually focuses on control theory. And I work across disciplines with psychophysiologists and cognitive neuroscientists to develop novel brain-computer interfaces. So to start out, I think the first question is, what is a brain-computer interface? I think in general, a brain-computer interface is any technology that accepts neural signals as either an input or that drives a neural system. And that could be a brain, or it could be a nervous system, it could be in an animal, it could be in a human. And there are a variety of ways that we acquire neural signals. There are invasive methodologies. This is one called ECOG, or electrocorticography. The skull is peeled back, and basically a fabric of electrodes are placed on the cortex. We can acquire neural signals through that methodology. There are microelectrodes which can be implanted in the brain. There are also non-invasive methodologies. This is called magnetoelectroencephalography. It measures very weak magnetic fields that are believed to emanate from the brain. And then there's electroencephalography. And this is the most widely used non-invasive method for brain-computer interfaces. It's what we use in our lab. It measures electrical activity on the scalp. And the main reason to use electroencephalography is it's very simple, it's very clean. It's not easy to use. There are some difficulties, particularly with the biophysiology, that we have to take into account, some of which I'll discuss in a moment. But in general, it's the most accessible and straightforward, passive, and friendly for human subjects. Oops. So an overarching question is, why study BCI at all? And there are a variety of reasons. BCI is actually a nascent field. It's just begun to take off. Actually, one of the first BCIs that was ever developed was in 1989. It's called the P300 Speller BCI. What it consists of is a display. Actually, I had it on the previous slide, where you flash letters, and you're able to detect at a subject. So the subject looks at these flashing letters, and you're able to detect which letter the subject is looking at by measuring electrical activity on the scalp. And for locked-in patients, people with ALS, people who have been paralyzed, this enables them to spell sentences, communicate with the outside world. So there's clinical impact for these devices. They provide a means of communication for paralyzed people. There's some speculation that they can also accelerate rehabilitation from damaged neural tissue, even the non-invasive case. What we can do is treat the human subject or a human patient as part of a feedback loop, interacting with a computer. We can design systems that may provide optimal feedback to help guide neuroplasticity through behavioral measures. And we can use the neural signals to determine what kinds of protocols might accelerate plasticity for damaged neural tissue. There are invasive methods which also try to bypass damaged neural tissue, reroute circuitry within the brain. Then there are various healthy human applications. Certainly there's a role of BCI in maybe augmenting video game applications. Workload monitoring is something that commercial enterprises have looked at for measuring biometric observation of workers. Battlefield biometrics, something the DoD is very interested in. BCI is also a means of studying neuroscience. We develop novel methods of studying neuroscience. We use BCI as a tool of inquiry to ask questions that neuroscientists may not actually be asking within their own field. And a final reason to study BCI, and I suppose pursue any research endeavors, to determine if it's worth studying further. What information do neural signals provide us that, say, behavioral measures, things that we can measure simply through the interaction or through the actions and behaviors of people, don't. So the technology that we use is EEG, and before I get into the specific paradigm that I'm working on, I want to do a quick overview of what these signals are and where they come from. So what does EEG measure? EEG measures the superposition firing activity in large populations of neurons, and over 95% of the activity that we measure on the scalp is believed to emanate in the cortex. And the cortex is the outer layer of the brain, basically. It's a very thin, just a few millimeter thick sheet of neurons. And these neurons, if you were to take this thing and stretch it out as though you had a napkin, these neurons are called pyramidal neurons, and they just point up like little antennas. They're orthogonal to the plane of that sheet. And so what EEG is you have basically all these little antennas firing off simultaneously, inducing currents that then pass through the scalp and through the skull. And we have voltages that we can measure over that surface, and that's what EEG is. It's generally on the order of about 30 microvolts. It's a very, very weak signal, and the frequencies that we work with are generally between, say, 1 and 40 hertz. There are higher frequency effects, but they're very, very low frequency. The frequency band that I'm particularly interested in is called theta band. Psychophysiologists have subdivided these bands, so if I use the word theta, what I'm referring to is frequencies between 4 and 8 hertz. Those are frequencies of interest. Another point that I think is really important is that EEG does not measure all of the brain activity. It tends to be preferential to what are called gyral sources. So if you look at a brain, you'll see all these little crags and valleys and rifts. Gyral sources are basically the peaks of these rifts. And it's the way the electromagnetics works out. So when we use EEG, we're not able to measure all of the activity in the brain. We're measuring some of the activity is hidden. Magnetoelectroencephalography measures the field orthogonal to the electric field. It tends to be preferential towards activity in sulci. So just something to keep in mind about the limitations of EEG. So the particular signals that I work with are called event-related potentials. And what these are imagine that you put a stimulus in front of a subject, and could be, I don't know, a choice of some kind the subject has to make. Subject presses a button. At t equal to 0, when when the stimulus is presented to them, this may induce a voltage deflection. And this is what such a voltage deflection might actually look like on the scalp. Now what you'll notice here is that the amplitude of this is extremely small. It's about 3 microvolts. And on the slide prior, I had shown that EEG activity in aggregate is usually around 30 microvolts. So these ERPs are buried in the noise. And the way that psychophysiologists find these things is they do hundreds of trials and they average them together. And so when we look at psychophysiology studies and somebody talks about an ERP, they're usually talking about an effect that's observed over many, many trials. So as a BCI developer, this is somewhat problematic because we'd like to have signals that we can measure at individual time points over time, so we can use that as a control signal in a system. So there are certain challenges inherent with this methodology. This signal also consists of several latent components which are spatially distributed across the scalp, and they sum up at points of measurement. Each component may relate to different behavioral activities, and that's what ultimately forms the overall morphology of the wave. So there's a lot of behavioral information encoded in these things, and what psychophysiologists try to do is modulate single components and then observe changes in the morphology. As BCI developers, we try to exploit that information to develop controlled systems. So okay, this is really the meat of the talk. A few months ago, this was, I think it was in May, it was the anniversary of Pac-Man, and I was playing it and I thought it would be kind of cool if I could just play it by looking at it, just by staring at it. Imagine that you had some idea in your head of how you'd like the Pac-Man to run around the board, and there he goes. If you have some idea of how the Pac-Man might in fact run around the board, can we detect your desired policy for that Pac-Man and somehow induce the Pac-Man to behave as you'd like him to? And that's the question that I'm currently working on right now. So what we need in order to do this is we need a neural signal that will critique the actions of the computer algorithm as he makes them. And fortunately, such a signal exists. It's called the observational feedback-related negativity. So a moment ago I talked about ERPs. This is an example of an ERP. And this is an error signal that's elicited whenever you observe an expert. So you're watching the Pac-Man game. The Pac-Man takes a turn towards a ghost. You don't like that. The instant he takes a turn towards the ghost, ERP. Okay? And that's what happens. We can measure the ERP. Now, I also mentioned a moment ago that these effects are usually averaged across multiple trials, and that's also the case for the FRN. But it turns out, and this is actually a very new methodology in psychophysiology, there's a theta burst, a burst of frequency between 5 and 8 hertz that co-occurs with these ERPs. So while this ERP is buried in the noise, we can very easily detect this theta burst, and it tends to always occur with this ERP. So on single trials, I can actually detect when you observe an error, and we can incorporate that into a control policy and exploit it in a system. And there's a very strong neural basis. To spare you a lot of the details, I'll just say that this is a signal that comes from or is elicited by what's called the midbrain dopamine system, which is involved in reward processing. It's located in this section of the brain, or it's part of the system is elicited, or is part of the midbrain dopamine system is what's called the anterior cingulate cortex, which is the frontal lobe of the brain, and that's where this signal is elicited from. So how do we detect it? This is pretty much the bulk of the signal processing that we do. This is from a study I ran back in November. Just a basic bandpass filter around the theta band. We do a Hilbert transform, compute the instantaneous power for each time sample, and then average the power within some window after the onset of the stimulus, and that window will be calibrated to a subject-specific case. And we measure this signal in a frontocentral location on the scalp, so approximately here. And here, this is just an example of a theta burst occurring around 400 to 500 milliseconds afterwards. This is observational feedback-related negativity activity. So to sum up where we're at, I've described a problem where we want to play a game by simply observing it. So we have some algorithm playing the game. You're observing the game, and you're generating these critiques of the decisions that the algorithm makes. And for the sake of simplicity, we'll just assume that you either see an error or there's no error. So it's a binary signal. So now we want to put this into a control formulation so we can solve the problem.
Sorry, can I ask a question?
Oh, sure.
So the way that you've described this, what you're measuring is in reaction to a fairly abstract concept. I don't like that.
Yep.
Somebody is watching an expert nature.
Yep.
So does that extend, for example, that maybe you put up the Hilbert transform and I immediately thought, ugh, a Hilbert transform. It's the same level of response that would be there, or is it a little bit more specific to?
It's context dependent, and it tends to occur on these like single trial choices. To give you an example, where you have maybe a countable set of choices at a time, I think would be the cleanest way of describing it. So yeah, one issue actually, and I'll address that later, is as the complexity of the problem increases, the models may not hold. So we're focusing on a very simple case. So what we're going to do here is we're going to model the human observer as an average payoff Markov decision process. The reason we're doing an average payoff Markov decision process as opposed to just a Markov decision process is the math works out a little bit better. But it ends up working out perfectly fine. And this Markov decision process is characterized by Bellman's equation. This is the average payoff form of Bellman's equation. So to sort of clarify some of this notation, if you're not familiar with it, the x's represent states of the game, say the position of the Pac-Man, position of the ghosts, the state of the actual game. A are the set of actions, so the actions that the Pac-Man can take at any point in time. This rho is the average reward per time step while following a policy pi. Policy pi is how we pick an action when we're in a particular state. Okay? So assuming we follow a particular policy, this represents the average reward we'd expect to receive in each state. And so what we have is these Qs, I didn't denote here, but these Qs are the state action values. That's the expected cumulative reward from starting in state X and taking action A in that state and following a policy pi out to infinity. So now if we know the Qs, okay, if we know the average reward the probability here, this is just the dynamics of the game. So this is if I start in state X, I take action A, the Pac-Man moves, the ghosts move to X prime. That's the next state. This is given. If we know the cues, the row, and the probability, we know the reward function. And if you have a Markov decision process and you know the reward function, you can solve Bellman's equation. And you can solve for an optimal policy, pi star. Okay. So in our case, the optimal policy, pi star, is to take the action for which we have the highest state action value. Because the bigger the state action value, since this captures cumulative reward from starting at state X and tending off towards infinity, we expect to receive the highest reward starting in this state. Okay? So the take-home point from this, without burdening you in details, is that we can characterize our observer with the Q values and the row. If we know the Q values in the row, we know R, we can solve for a policy pi, which means that for every observer, an observer may have any Q values or row, we can solve for a policy pi, is the basic take-home. So to simplify just what I just said, this is basically what the problem is. We have a human observer. He's characterized by his Q values in his row. And we want to design an agent that implements this policy pi, okay, the optimal policy pi. So we model this as this interaction effect where our agent he's implementing the policy, so he's taking actions, and our human observer is generating observations, so that the state of the game is changing, and he's eliciting those error signals. We want to take these error signals and use them to compute the optimal policy pi star. So just a clean statement of the control goal here is to design an agent which is optimal with respect to an unknown human observer that is modeled as an average payoff Markov decision process. And this is an adaptive control problem because we don't actually know what the environment is. We don't know what the Qs and rows are. We need to guess them in order to achieve the optimal policy pi star. Oops. Keep doing that. Okay, so there's a result in the control literature, it came out in mid-May by Dan DeBron and Peter Ortega, called a minimum relative entropy principle for learning and acting. And it's a very elegant result called the Bayesian control rule. And it solves exactly the problem that I just described. It will construct an adaptive agent that's universal with respect to a given class of experts. So we made an assumption that our human observer is an average payoff Markov decision process. That is the class of environments that he resides in. So what this rule allows us to do is find a policy which is optimal with respect to that class. And the way it goes about it, the details, I don't have tons of time, but the details are that it minimizes the relative entropy of the adaptive agent from the expert that is most suitable for the unknown environment. And under some weak assumptions, it will always converge to the control law of the most suitable expert. So with regards to the last slide, we can always achieve the optimal policy pi star for our agent. And the algorithm is actually fairly simple to implement. You're just constructing a posterior on the models for the environment, in our case the human observer, characterized by the Qs and rows. We have an intervention model which describes which action we should take. We then observe the response from the environment, and we just keep updating the posterior on our model. This gradually contracts to the environment that we're actually observing, and we end up implementing the policy pi star, which is the optimal policy for this human observer. So we designed this really simple game. Basically, we have a waterfall plot here. So these little yellow blocks just fall down. It's kind of like Tetris. And the goal for the observer is they want the green block to avoid the little yellow blocks. That's the goal. And if they collide with the block, that's a bad action. All right. So we simulated this here for several cases. So the blue trace here is a case where there's no noise in the reward. So the reward is true, and that's the error signal. The reward function is actually the error signal coming from the human observer. And so since this is a deterministic problem, you can always take the right action, and you can always get a point of 1 at every time step. So what we see here in the algorithm is starts off and it converges to 1, the average reward of 1, which means that the algorithm is working. There's noise because it's stochastic. We're sampling. We're doing some Gibbs sampling underneath, and we're sampling distributions. But over time, the posterior continues to contract. And then as we add noise to the reward function, which is what will happen when you have an online human, because there'll be misclassifications. The dynamics of the FRN are actually far more complex than I've actually just described. But so there'll be some noise. You have suboptimal cases, but it still converges to optimal policies for each suboptimal case. And it does so in few trials, actually. This is, say, 100 trials. In each case, we're within some bound, which is excellent, because it's about 2 seconds for each trial. So that's, say, 200 seconds to converge to the optimal policy under this scheme. So it's very, very, very lean, very nice.
I have one more question.
Oh, sure.
So this idea of the noise, that takes into account situations where the human just ceases to pay attention for some amount of time.
Well, that'll change the dynamics. Yeah, basically this noise are just false positives or false negatives in aggregate. So if the subject ceases to pay attention, the statistics might change. And if the statistics are changing, that is a good question.
The reason I ask is because in visual psychophysics, which is what I do, you almost have to model that some amount of the time your observers are not doing what you have asked them to do.
Right.
And even though you're getting responses, those responses are going to be meaningless.
Uh-huh.
And that substantially improves all of the response modeling.
Okay, yeah.
Which is why, I wonder, maybe because they're active here, it's a little bit more, they tend to pay attention for a longer period of time. I don't know.
Yeah, I think one issue that I've actually had with this paradigm is that people continuously say they get bored. And I need to make it more interesting. Like, people would rather play the Pac-Man, but it's just way too complex to model. So, yeah, so making interesting interfaces is a difficulty. What I'm working on now is, as I mentioned, the feedback-related negativity is actually, the dynamics of it are significantly more complex than what I've just described. And there's actually, the human is actually learning about how the agent behaves while he's interacting with it. So he's building this model of what the agent is doing, and some of that information is being encoded in the feedback-related negativity. So what I'm working with right now is trying to model that learning process. And what we've decided is that the cleanest way to do it is to treat it like a controlled Markov decision process with some latent state variable Q. And we're trying to figure out what the dynamics of that should be. And I'm designing a number of studies follow-up studies of just basic psychophysiology learning experiments to better understand the dynamics of the feedback-related negativity and determine what a good, solid model for that will end up being, so that we can properly model this interactive effect between the two. And that's basically my talk. I hope it wasn't too confusing. I'd like to thank Tim Brettel I collaborate with. He's in the Department of Aerospace Engineering, and Ed Macklin over at the Beckman Institute, and also James Kavanaugh at University of Arizona Psychology Department. We've had a lot of informal discussions about the FRN, all the folks in my lab, and NSF for funding. So thank you very much.